In the previous video, we obtained the equation for the position vector for center of mass, and it was RCM. The position vector for the center of mass of a n particle system is given by RCM is equal to 1 by m sigma mi ri, I is equal to 1 to n, right? And in this video, we are going to look at the Cartesian components of the center of mass. So let's once again refer to this diagram. This is an object with n particles. We've shown a few particles in this. This is the center of mass C, particle 1, 2, particle n, and these are their respective position vectors. R1 position vector for particle 1, RCM for C, R2 for particle 2, and position vector Rn for particle n, right? So let's move ahead. Now RCM, right, the position vector RCM can be written as, you can write is that XCM I plus YCM J plus ZCM K. So I can represent any vector in the form of its orthogonal unit vectors. Just for reference, I have written over here, if there is a vector A, it can be represented by AX, I, AYJ, AZK. These are the components of vector A on the x-axis, on the y-axis and z-axis, and these are the orthogonal unit vectors. So it is possible to represent any vector in the orthogonal unit forms in this particular way. And we are doing the same thing over here. RCM, which is the position vector for center of mass, has been represented in the form of its orthogonal unit vectors. Similarly, Ri, that means the position vector for any of the particles 1, 2, 3 up to n, can be represented as x I plus y I j plus z I k. Right? Let me give these equations name. Let us call this equation 1, let us call this equation 2, and equation 3. Now I'll put equation 3, that is the value of Ri, in equation 1. So I'll put this value of Ri in equation 1. So here Ri, I'll put this particular value. So I'll get RCM. The equation 1 will now become RCM is equal to 1 upon m sigma mi. For Ri, I'll write down xi plus yij plus zik. Therefore, RCM now will become equal to sigma of mi xii, right? You can write upon m plus yi mij goes upon m plus zi mik upon m. And this can be written as RCM is equal to sigma of mi xi upon mi plus sigma of mi yi upon mj plus sigma of mi zi k upon m, right? Basically opening up this bracket. So let us call this equation number 4, right? I hope you got this, right? 1m, the m I have taken it out for all the terms over here, and we have multiplied mi with, or basically we have multiplied mi and m with this bracket. So I get this equation 4. Now let us compare equation 4 and equation 2. So both is equation for RCM. Here I have got XCM, and here also I have got this particular term, and I have got I over here and I over here. Similarly YCM, and I have got here a term which involves Y and unit orthogonal vector J. Here I have got unit orthogonal vector K, and here also I have got K, and this term involves Z. So if I compare these two equations, I get the value of XCM as this particular term. I and I are there, so XCM is this term. Similarly, YCM is this term, and ZCM is this term. So I'll write down XCM. Before that, let me write down comparing equations 2 and equation 4. Equation 2 and 4, xcm is equal to sigma of mi xi. Of course I can take 1m, I is equal to 1 to n. Ycm is equal to 1 upon m sigma mi yi, I is equal to 1 to n, and zcm is equal to 1 upon m sigma of mi zi, I is equal to 1 to n. Thus, I have obtained the Cartesian components of the center of mass. The Cartesian components of center of mass are xcm, ycm and zcm, and I have obtained their values xcm, ycm and zcm. So, we'll keep them in a block and say these are the Cartesian components